Can everyone hear me? Is that working?
They can. So yeah, the microphone, they face backwards, but you probably won't hear them as well as the crowd does.
That's very strange.
Okay. Hello everyone, welcome. This is the busiest evening we've had all year. It's wonderful to see so many people come out to hear about astronomy. I think all of you have heard the bad stargazing news so far, that we're not going to be stargazing, but we're going to have a wonderful headline talk, all Dr. Seuss themed planet talk, which I've never seen before, which is very exciting. Followed by some tea and biscuits and refreshments out in the lobby, and then a second talk afterwards. The one thing I will mention, the one bit of housekeeping before I hand you over to our speaker, is that some of you might be aware, as part of the Cambridge Festival, we do an open day, and this year it's on Saturday the 18th of March. And so the whole department is going to be open between 2 and 6 in the afternoon, and there's going to be a whole programme of games and talks and planetarium shows and activities and all kind of astronomical fun. So there's going to be more information on our website with exactly what's going on, but the date for your diaries is Saturday the 18th of March, right here from 2 to 6 p.m. It's going to be a really great day. Cool. So I think all that said is to hand over to our main speaker, Dr. Emily Sandford. Sorry, I'm overwhelmed.
All good.
Dr. Emily Sandford is going to be telling us all about planets you can go to. So big hand for Emily. Have you on the lights, by the way? Do you want the lights on?
I don't mind. It's fine if this is how it's usually.
Are you happy with this?
Yeah, this is good. Yeah. Awesome. Thank you all so much for coming. I'm a bit overwhelmed to find out how oversubscribed the auditorium is today. I'll do my best to deliver. As Matt said, my name is Emily Sandford. I'm a postdoc here at the astronomy department. My own research is about exoplanets. So these are the planets that orbit stars other than our own sun. And this is a brand new field. It's only about 25 years old. That's when the first exoplanet was discovered back in 1995. And we know a lot more now, but we still have so much to learn. So I'll tell you a little bit about it today. So I'm going to start with the close to home, the planets in our own solar system. The solar system, only one system, but it has a fantastic variety of different worlds. And I'm just going to step through a few different, all the examples of planets in our solar system, and just give some brief notes about what they're made of, what sort of makes them special and unique. And then for the rest of the talk, we'll be discussing how we know that. So that's the more interesting question. We have all these observations of worlds in our own solar system and elsewhere. How do we know what we know about them? So outward from the sun, the first planet we have is Mercury. Mercury is the smallest of the planets. These will not be to scale. I just needed them to nicely fill up the slide. Mercury is a really extreme world because it's so close to the sun that the sun's wind has blown away whatever atmosphere Mercury once had. So Mercury is just a bare rock like the moon now. That means it has very extreme temperature variations on its surface. So in the shadow on Mercury, it's really cold. There's ice, minus 150 degrees Celsius, but in the sun, it's boiling hot, 400 degrees. So just by stepping from the shadow to the sunlight, you're experiencing a 550 degree temperature swing, which is very, very extreme. Next, we have Venus, which is actually the hottest planet in the solar system, despite not being the closest to the sun. The reason it's so hot is because it has a very thick blanket of carbon dioxide in its atmosphere that's insulating the surface. And so it's like Venus is wearing a blanket. In fact, it's so hot and so the atmosphere is so thick on the surface that it'd be like you're swimming 3,000 feet below the surface of the ocean, and if you tried to cook a pizza, it would only take you 10 seconds. It's really, really hot. Next, of course, we have our home. We have Earth. Earth is the only planet that we know to host life in the solar system, so that already makes it very special. Geologically, it's the only one that we know of with surface oceans. So we think those two things are related. We think the presence of a liquid like water on the surface is very important to the development of life, but we only have one observation of life so far, so we can't really confirm that. Next, we have Mars. Mars, the red planet. The red color of Mars gives some hints about what it was made of, what the soil was made of, before we ever confirmed that. So the iron color comes from rust. So just like rust is red on the Earth, the red color, I should say, comes from rust. When iron rusts on Earth, it turns red, and the same happens in the Martian soil. So that's why it's called the red planet. Next, we have Jupiter, which is the largest planet in the solar system. Jupiter is about 10 times the radius of Earth is, so you could stack up 10 Earths to make the height of Jupiter. Jupiter has these incredible weather systems. It's got a very, very thick atmosphere of helium and hydrogen, And all of these weathers, you can see in particular the big red spot, which is just a big hurricane about the diameter of Earth. All of these weather systems we think come from ammonia sort of swirling around in the upper layers of Jupiter's atmosphere. We're most familiar with ammonia on Earth as a surface cleaner. You've probably encountered it in your daily life, but it's making incredible patterns in the clouds of Jupiter also. Next we have Saturn. Saturn's most distinctive feature are these beautiful rings, which come from water, ice, and carbon dust. The Cassini mission went to Saturn 10, 15 years ago now, and it sent back just the most stunning photographs that I've ever seen. So we'll show a couple more of those later in the talk. Next we have Uranus, which is a beautiful light blue color. This light blue color comes from methane in its atmosphere. And finally Neptune, which is also blue, also because of methane. The difference in color between Uranus and Neptune was an unsolved mystery until last year. This was something that was first observed when we sent satellites out to these planets back in the 80s. We had the Voyager missions. We now believe that it's because the methane layer is thicker on Uranus than it is on Neptune, and that explains the color difference. But again, the chemistry of clouds is very complicated, so that was a recent discovery that we'll talk about a bit more in the future. I also have to talk about Pluto, beloved Pluto, demoted from planet status because of its moon. So Pluto has a few moons, but its main one is Charon. And Charon is so big compared to Pluto that we don't have actually Charon orbiting Pluto the way the moon orbits Earth. They're so comparable in size that they actually really orbit each other. Their center of mass is between them instead of within Pluto. So that's why Pluto was demoted. But it's still a fascinating place full of fascinating chemistries and compositions. We know now that this white stuff on the surface of Pluto is snow, but it's not snow like we have on Earth. Pluto is so cold that this is actually frozen nitrogen snow. So you could go skiing on Pluto, but it would be a very different experience from going skiing here on Earth. And these are not the only worlds that we have in the solar system. There are also dozens of moons orbiting the various planets. I just want to highlight a couple that are super interesting. For the moons of Jupiter, these are only 2 of the 4, but we have, or Jupiter has many, but 2 of the 4 largest. We have Europa here on the left. Europa has a surface crust of ice, and below that we think a subsurface ocean, which would be a very exciting place to look for life. And on the right here we have Io, which is a volcanic world. So Io has 400 volcanoes on the surface that are spewing sulfur all over the surface all the time. Much less pleasant, perhaps, for life than Europa is. And then below this, I'm just going to highlight 2 moons of Saturn. Again, Saturn has many moons, but these are my favorites. We have Enceladus here. I've started because we'll come back to Enceladus later in the talk. Like Europa, it has an icy crust and potentially a subsurface ocean. And then we have Titan, and Titan is covered in this beautiful methane haze that looks like a marble. Titan is super exciting because it has lakes on its surface, lakes of methane. So it's, in some ways, very similar to Earth in that it's got liquid and gas going on its surfaces. It's not water, it's methane. But that chemistry could lead to some really, interesting possibilities for life in the future. So the question is, how do we know what these worlds are made of? So I've told you a little bit about what they're made of, but the more interesting question is, how do we know that? There are kind of 2 options for how we can figure out what something is made of as scientists. We can either go to it or not. That's all we got. We can either go, we can put people or robots on the surface of the world and actually test what's there, or we can look at it from a distance. And those are the only 2 choices we have. As far as going, there's actually a surprising variety of worlds in the solar system that we've been to. Obviously, we live on Earth, so we know what's on Earth's surface very well. We can look at it, we can test it, we can analyze it. We've sent people to the moon, of course, so Earth and the moon are the only 2 astronomical bodies so far that have had humans standing on the surface. But we've sent robots to Venus, Mars, Jupiter, and Titan so far. So Venus, we've dropped probes into the atmosphere that have landed on the surface. Jupiter has a very thick atmosphere and nothing like a traditional surface, so you just drop a probe in and you watch it until you can't see it anymore. And Titan, as I said, the Cassini mission went and looked at Saturn, and it dropped a probe, the Huygens probe that landed on the surface of Titan. That was a very recent thing. In the near future, we'll be sending a probe to Europa, so that's the moon of Jupiter that has the icy crust in the subsurface ocean. And there's also a very exciting mission to go back to Titan. It's called the Dragonfly mission. And Dragonfly will fly essentially a little drone helicopter all over the surface of Titan and sample what's in various of the lakes. So that's upcoming. That's going to be in the late 2020s that launches, but it's very exciting that it's on the horizon. I have an exclusive picture here. This is from NASA of the Perseverance rover. Oh, I'm sorry. There we go. So this is the type of craft that we're sending to the surfaces of other planets. It's about the size of a car. It's a lot bigger than it looks in the picture. And it has all these instruments on it that can analyze various features of the surface and take very, very detailed photos and maps so that we understand things better. So it's very exciting that in the near future we'll have comparable data to what we're getting back from Perseverance from the moons of Jupiter and Saturn. It's a very exciting development. But what happens when we can't go to another world? What happens when we can't send a person or a robot, if it's just too far away, or if it's too inconvenient, or it's too difficult to get there, which is the case for almost every other body in the universe? How can we tell what's in something if we're only able to look at it, which is really our only option that's left? So in order to answer that question, I'm going to need to take a little detour and talk about color. So how can we use the color of something to figure out what's in it, which is obviously a skill that this character wishes he had. Let's start with the sun. So here is a picture of the sun. The sun produces white light. So it produces light of all colors. Our eyes perceive that as white light. And if we stood in space and we looked at it, it would look white. In this picture, it looks like a fiery yellow color. That's actually a false color. This image was taken in the ultraviolet band, which is a color that our eyes cannot perceive. It's sort of beyond the purple. Our eyes can't see it. So this was taken in the ultraviolet, and then it was translated into yellow so we could perceive it with our eyes. If we looked at this picture of the sun through a particular filter, let's say we had glasses that had yellow lenses in them, it would look like this. And in fact, whenever we look at anything with our eyes, through a telescope, through a camera, through a filter, we're looking through some kind of filter. So as I said, our eyes can only perceive the visible colors, so that's between red all the way to violet. That's a sort of natural filter that's already placed on everything that we can see in the universe. The sun is emitting colors way beyond that range, but we just can't perceive them directly. We have to build instruments that can perceive them instead. And the color that we perceive when we look at something is a combination of the colors that are coming off that object in the first place, and also what's going on inside our eyes and between our eyes and our brains. So our eyes have 3 different types of cells in them. We have cells that can see red light, green light, and blue light. And when various combinations of these cells are activated in our eyes, then we perceive that combination as different colors. So when our eyes are activated in the green and the blue and the green, we perceive that combination color as cyan. And when all 3 are activated, we perceive that as white light. So just to hammer this point home, we have this white fish. That means it's reflecting all colors, and when we look at it, our eyes are activated in the red and the blue and the green. For the green fish, it's reflecting green, but perhaps it's absorbing the red and the blue, so we're only seeing the green light that comes off the surface, and so on and so forth for the red and the blue fish. This is a really useful, it sounds basic, but it's really useful because the colors that a particular object reflects versus absorbs are determined by what molecules and what atoms it's made of. So by looking at what colors are reflected and what colors we perceive coming off an object, we can work backwards to figure out what the object is made of. We can actually get much, much more specific than just red and green and blue. Those are quite vague. You know, my shirt here is red, but so are the seats. There's lots of different colors that fall under red. So we have to be very, very specific if we're trying to identify exactly what atoms and molecules are in a particular substance. So let me explain exactly what I mean by that. Everything is made up of atoms. This is the simplest picture of an atom that you can imagine. We have a nucleus, then we have 1 electron that's orbiting. And the funny thing about atoms is that this electron is only allowed to orbit either here or here. It can't go anywhere in between. And in order to make this jump, it has to absorb exactly enough energy to bump it up from this level to this level. If it absorbs a little bit too much, it won't make it. A little bit too little, it won't make it. And so the amount of energy it has to receive corresponds to a very, 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 very specific color of light. So if a ray of light of that very specific color hits it, in this case we have a purple, then it will bump up to the next level, it'll absorb that color, and then we won't see that color bouncing off that atom. So if very, very specific colors are missing, we can work backwards to figure out what atoms must be absorbing those colors in order to remove those colors from the light we would otherwise see. To make this a little bit more concrete, I'll just show you what happens when we look at the sun's light. So if we run the sun's light, which again is white, through a prism, we get this beautiful rainbow all the way from the red all the way to the purple. But if we zoom in on this rainbow, what we find is that very, very, very specific colors are missing. So we're not seeing all the potential reds. We have a red that's missing right here, another red that's missing right next to it. We have several that are missing in the sort of orange to yellow region, and so on and so on and so on. By doing experiments in the lab where we put various atoms and various elements in a box and shine light on them and see what colors of light are missing, we can match up the missing light from the sun to what we know are the colors that are absorbed by specific types of material. So in this case, we know that oxygen must be present to absorb these particular colors out of the sunlight, and so on for sodium, iron, calcium. There's lots of things that are present in the sort of outer layers of the sun's atmosphere that are responsible for these missing colors. A fun fact is that one of these, or some of these lines are due to helium, the atom helium. Helium is called helium after Helios for the sun, because it was discovered on the sun before it was ever discovered on Earth. So people looked at the sun's light through the prism, they saw that certain lines were missing, they didn't correspond to any known substance from Earth. They posited, okay, there must be something we've never discovered that's absorbing these particular colors, so they called it helium, sort of unknown solar substance, and then about 5 years later it was discovered on Earth. Okay, that was a bit abstract. That is, I promise, the only trick that you need to know to understand exactly how we're going to figure out what's going on in the compositions of other solar system bodies, and in fact in exoplanets as well. And it turns out that this trick of looking at colors and matching them to substances is incredibly useful, and it's going to allow us to figure out not only what the surface is, that is the ground and the atmospheres of planets are made of, but also what their insides are made of, and that's really exciting. So thing one, we're going to figure out what the outside of a planet is made of, and thing two, we're going to figure out what the inside of a planet is made of, and we're just going to do it with this one weird trick of color. All right, let's start with the outsides. This one is in some ways simpler, just because when you're looking at the outside of an object, then yes, like what you're looking at is in fact what's there. You don't need to do another sort of step of abstraction. In the solar system, I'm going to return to Neptune, my favorite. I just think Neptune is the most beautiful color of any of the planets in the solar system. We know that this blue color is due to methane, as I said before, because we flew the Voyager probe past Neptune. It took this beautiful picture. Voyager had a prism on it that analyzed the light that was being reflected off of Neptune. And when you looked at the missing colors that were being reflected off of Neptune, you saw that the missing lines corresponded to methane very, very strongly. And as a result, you can conclude that there's a lot of methane present on Neptune that's giving it this blue color. You can use this trick even more specifically, so we're going to return now to Enceladus, which is the moon of Saturn that I mentioned earlier. In this picture, this is one of the beautiful pictures taken by the Cassini mission. The sun is somewhere up here, so you can see that this is the day side of Cassini, and then you see here we have the night side down here. If we look at a different view, we now see the sun is sort of back behind in this direction, and we're looking at Enceladus backlit by sunlight. And it's illuminating these beautiful plumes of gas that are coming off of Enceladus' surface. And you can use this same trick, looking at the missing colors of sunlight as filtered through this gas, to work out that this gas is made of hydrogen. And because we think that Enceladus has a subsurface ocean, the sort of most promising explanation for that hydrogen is that it's coming out of hydrothermal vents in the ocean. That's really exciting. On Earth, we have similar hydrothermal vents, and they're a really exciting place to look for life, because life that can't get energy directly from sunlight can get energy from the heat coming out of hydrothermal vents. So if similar things are present on Enceladus, it could be a very exciting environment for alien life. Okay, so that's how we study the surfaces and atmospheres of worlds within our own solar system. I'm now going to explain how we can use the same trick to figure out what planets in other solar systems are made of. I need to take a little detour into how we discover these worlds in the first place. So this is a cartoon that illustrates the most fruitful way so far of finding exoplanets. It's responsible for something like 5,000 exoplanet discoveries so far. All you do is you look at the amount of light that's coming from a star over time. And if temporarily there's a dimming, then you can infer that that dimming might be due to the shadow of a planet as it passes between that star and our telescope. And because planets orbit around and around like clockwork, if that dimming repeats itself over and over, you can say very strongly, okay, this is probably due to a planet, and we're just seeing its shadow over and over again as it casts that shadow on our telescope. Unfortunately, all these stars are so far away that all of this activity is taking place within 1 pixel. You can't see that beautiful cartoon of the stellar surface with the planet crossing in front of it. You can only see this curve, this traced out amount of light versus time. But even that is actually enough to work out what the planet is made of, which is really, really exciting. So the relevant feature of it is how deep is this, as we call it, transit event? How big is the shadow that the planet is casting on our telescope? So if the planet is big, the transit will be deep. If the planet is small, then the transit will be shallow. I'm going to tell you about one transiting exoplanet in particular. This is a planet that, in the great tradition of naming planets after Roman gods, is called GJ 1214b. We had an observation of its transit from a mission called Kepler, and we knew that made it sort of between Earth and Neptune size. So it's intermediate in size between these two known solar system bodies. Already that makes it really weird. It's not like anything in the solar system. We don't really have anything in the solar system that's intermediate in size between Earth and Neptune. So the question became, okay, we don't have any analog of this in the solar system. What is it like? What is it made of? A team led by Laura Kreidberg, who was then at the University of Chicago, pointed the Hubble Space Telescope at this planet and its host star. And what they did is that they observed that transit, the shadow that the planet was casting, in many, many different colors. So here they're colored from purple to red, but all of these colors are in fact in the infrared, so they're all too red for the human eye to see, but Hubble can see them just fine. It's going to be extremely difficult to see it with the eye, but there are actually very subtle differences in the depth of these transits in the different colors. And the differences in those depths can tell you what the planet is made of. So if I plot this in a different view, here we're looking at how deep the transit is, so how big the planet looks when you look in that color, as a function of the color. So in this color, the planet looks small. You go a little bit bluer, the planet looks big, small, big, et cetera, et cetera, et cetera. And alongside this data, so the observations of the planet are the black dots, we have 3 predictions for what the data should look like if the planet's atmosphere were pure methane, pure water, or pure carbon dioxide. And you can see that the data doesn't match any of these curves very well. None of these curves explains the data. And the reason for that, in fact, the data looks pretty much like a flat line, which I imagine was pretty disappointing to Laura Kreidberg's team at the time. But what that means is that, in fact, this planet is cloudy. Instead of seeing a nice, clear signature of any one chemical in its atmosphere, we're seeing the very confused, sort of flat, indistinct signature of hazy clouds. And so this is an observation of clouds on a world that doesn't orbit our sun, which is very, very exciting. So that's how you work out the atmospheres of exoplanets. You can take it one step further and even find out what the interiors of exoplanets are made of. You need 2 ingredients in order to be able to do that. So you need to know how big the planet is, that is, how much space it takes up, what's its volume in space, which we know if we have a transit observation of the planet. And then you also need to know how much it weighs. And if you know these two things, you can compute how dense it has to be, and then you can compare it to say, okay, if a planet were made of pure iron, which is like the densest thing you can imagine, here's how dense it would be. And if it were made of water, which is much less dense, this is what it looks like. And you can compare what you observe for the planet to those extremes and sort of work out where it must fall in that continuum of possibilities. So as I said, how big the planet is comes from its transit observation. How heavy is another method entirely. So how the heck do we figure out how heavy a planet is? Let's see if this works. The trick to this is just like Pluto and Charon orbit each other. In fact, a planet and its host star are orbiting each other too. It's not that a planet orbits its star, it's that the planet and the star orbit their common center of mass. And as a result, as the planet is orbiting around, so we have the planet here, the star is orbiting around too, opposite the planet. The planet is too dark to see. They're small and they don't glow very brightly, but we can see the star, and we can measure the colors of light coming off the star. And because of an effect called the Doppler effect, when the star is moving towards us, its light looks bluer, and when it's moving away, its light looks redder. So I'll replay this again in a second. But the Doppler effect is actually, should be familiar to everyone, because we experience it on Earth with sound waves. So it happens to light waves too, but let's see if the sound of this works. Oh no. Right, has everyone heard this in real life? I hope that was loud enough for people in the back to hear. When the car is moving towards us, it's got a high-pitched horn sound, and then when it passes us, it sounds lower-pitched. And that's the same effect of waves getting squished when they move towards us and stretched when they move away. So I'll play the cartoon again. Excuse me. I won't play the cartoon again. But we can watch the light do the exact same thing. So as the star is moving towards us, it looks blue. As it moves away, it gets stretched out and looks red. And that can tell us, based on how fast it's going and how much it's swinging back and forth, that can tell us how heavy the planet must be to be pulling on it. Okay, so from the transit, we know how big the planet must be. If we also have these Doppler measurements, we know how heavy the planet must be. We can combine those two things together to estimate how dense the planet is. And then we can compare to, as I said, a bunch of different expectations for potential compositions of the planet. So what we're looking at in this plot, we have the mass of the planet, so how heavy it is on the x-axis, how big it is on the y-axis. And then these curves tell us what we would expect for a planet that was 100% iron, half iron, half rock. So magnesium silicate is rock, 100% rock, half water, and so on and so on. So you can see Venus and Earth are both here. They have actually very similar densities. Earth is mostly rock, but it's got some iron, which pulls it down, and then some water, which pulls it up. So that's why it lands roughly here on the plot. On this plot also, we have GJ1214b. So this is the planet that we just talked about being cloudy. And GJ1214b falls, it's less dense even than a pure water planet, which should be impossible. We don't think that planets can be that light. But the reason for that is that it's got this extended, as I said, cloudy atmosphere. It's like a big beach ball. It looks a lot bigger than it actually is because of these huge clouds that are making it look big and puffed up. So this was work that was led by Courtney Dressing at Harvard, I should say, to compile all these measurements and compare them to the expectations. So all of this is really new. All these measurements have really only been possible for the past 10 years. It's a really exciting frontier. Specifically, new space telescopes like the JWST, which launched this past summer, will be able to refine these measurements and give us much more precise ideas of what planets are made of. So it's an exciting thing to follow in the news if you're interested in it. And all of these possibilities open up really interesting questions for what life might look like, where we might find it, where these planets are forming and why. And I think it's a really exciting thing to talk about. So I'll stop there and I'll take questions. Thank you very much.
maybe just a couple of questions.
I know, yeah.
Sorry, just a couple of questions because there's an angry horde outside who want to see all this wonderful science as well. Yeah, who's got a question for Dr. Sandford? Right at the back.
That's a really, really good question. It's going to be about half and half, because at any particular time, half of the planet will be facing the star, and that'll be the hot side, and half will be facing away, and that'll be the cold side. But depending on how mountainous the planet is, like how much opportunity there is for shadows, so if there's big steep mountains, you can have shadows that last all day because the sun never shines down into the valleys deep enough. You can have more shadows and more cold than you would otherwise expect. And we don't know how mountainous other planets are going to be. We see a lot of mountains in the solar system. So we think there probably will be lots of mountains on other planets too, but we don't know yet.
And one more question for you guys. How about you, Johan?
How much moons does Saturn have?
I think Saturn has between 70 and 80 moons at last count. There's a lot of them. And it comes down to, at a certain point, they're so small that you start debating what counts as a moon and what just counts as like an asteroid. And so it's exactly the same debate that people have between planet and moon, but sort of scaled down. Yeah.
Wonderful. Okay, so the logistics now, if you guys can all come out of this door and then the second audience can come in the top.
Awesome.
You guys still have to
Yeah, yeah.
For the slide where you were talking about, I think it was composition against Earth radii.
Yes.
I
Yeah.
think it was magnesium silicate you said.
Yeah.
Is that just because on average, or is it?
Yeah, it's just, rock has lots of different compositions, and astronomers are kind of lazy. So they're like, let's just choose one that can be our baseline rock. Yeah, it's very common, and it's got a density that's comparable to sort of average for rock, and so that's why they use it.
Thank you.
You're welcome.
You,
You're welcome.
if you want to go and take a 5-minute